Hello, dear students. So let's start today's topic of your next chapter, that is your electrostatic potential and potential difference, and the other is your capacitance. Okay. So, in yesterday lecture, I have already told you about electrostatic potential. What is that? That is only your work done required to move a unit test charge from infinity to a specific point against the electric field. Okay, so we will continue our discussion in this lecture and see that what are the next topics. Till now, we have covered this NCERT portion of class 12th, that is your 12th physics, and first chapter was completed, that was electric charges and fields. You can go and watch the lecture of that chapters. If you have not seen, you should go and watch that on GoAskNow Academy. And here, let's start our discussion further. Okay, so what is we have talked just now, that was electrostatic potential. The next topic is electrostatic potential difference. So here, you can see that one term is come or adding here, that is a potential difference. So it is some difference between 2 points. So there was one point was infinity or infinite point, and the second point was a specific point. But here the 2 points should be finite. There are some points which we can plot it and get the result for that. So let's read out the definition of that. So here it is written that electrostatic potential difference between 2 points P and Q. So if I have 2 points P and Q of a charge configuration consisting of charges Q1, Q2, Q3, Q4, and Q. So these are like charges. They are in any space Q1, Q2, Q3, Q4, and Q is and there is a Q charge also here. Okay, so these are like charges in that space where you have to find the electrostatic potential difference, and the point P and Q will be like any 2 points that are situated in the field of these charges. Okay, so you can see the diagram also here. What you can observe that there is P point and Q point. Okay, so what is the definition further? Let's see. So, and Q is equal to work done by an external force in moving a unit positive test charge against the electrostatic force from point Q to P. So, if I have Q and P 2 points, then there is some work done against this field. The field will be of these charges, and I have to do the work against this field to move the unit positive test positive charge from Q point to P point along any path between these 2 points. Like I can move from this path also, I can move from this path also. There is any path I can move on. Okay. So figure shows that the work done on a test charge Q naught. So if the test charge is Q naught, and why the electrostatic field due to any given charge configuration depends only on the position of initial and final. Okay, so you already know that your electrostatic force or that same is what it is your conservative in nature. Okay, so work done is independent of the path chosen in going from Q to P. So this is your statement of this electrostatic potential difference. Okay, so let's see what is next. If VQ and VP are the electrostatic potentials at Q and P. So if the points Q and P have electrostatic potential that has value VP and VQ, means that electrostatic potential at VQ will be what? By definition, electrostatic potential is what? That if a point test charge is there or a small test charge is there, then if I move it from infinity to point Q, then the work done in that process against the field is called what? The electrostatic potential. So that value is what? VQ. And that is, and the similar value is for VP. So here the potential, electrostatic potential is VQ, and here is VP. Okay. So delta V is assume that the your electrostatic potential difference between this path is delta V. So delta V can be denoted as Vp minus Vq. It means that what is the final potential you are getting here, electric potential, and what was the initial electric potential. The difference of that will give you potential difference between these 2 points. Okay. So that delta V can also be written like WQP upon Q naught. Okay, this is the by definition of electrostatic potential only. So that is analogous to that. So here work done in during this path QP, Q to P upon the test charge Q naught is there. Okay, so this is your second formula for that, and Vp minus Vq is like general formula for this. Okay, so let's move further and see what is the next there. So yes, the dimensional formula for electrostatic potential difference is given by, so it is similar to what your electrostatic potential only, because there also W by Q was coming. So ML2 T minus 3 A minus 1 will be the like dimensional formula for this also. Okay. Now the SI unit of electrostatic potential difference is volt. So it's potential like the SI unit of this is equal to volt only. So that was also of that electric potential, electrostatic potential. Okay. Thus, electrostatic potential difference between any 2 points in an electrostatic field is said to be 1 volt when 1 joule of work is done by an external force in moving a positive charge of 1 coulomb from one point to the other against the electrostatic force of field without any acceleration. So that is the clear definition of electrostatic potential difference. That it is what it is like when 1 joule of work done is done by an external force in moving a positive charge, because there are some charges like their configuration are like that, and here some electric field will be like there, like that some electric field will be there. So you have to like, if you move any test charge against this field, because this field will exert force like this on this charge, so you have to move in this field like this. So you apply some external force, but this external force is very like just opposite to like this force, means that F external is here equal to what? F field. What is the like force due to field? So you have net force will be equal to 0. So net acceleration will be equal to 0 only. So that is why it is written there that against the electrostatic fields of electrostatic force of field without any acceleration. That there will be no acceleration. The charge will be moving very slowly with constant velocity. Okay, that is why it is written here that acceleration is 0. Okay, so that is the definition of your electrostatic potential difference and definition of 1 volt also. So I hope that you got these points. Let's move further and see some examples of this definition. So I should remove the drawings here. Yes. So example 2 is there that a potential difference between 2 points is, just a second. Yeah, is 20 volt. So there is a there are 2 points and the potential difference between them is 20 volt. How much work will be done in carrying a charge of 400 microcoulomb from one point to one another? So if you have like delta V is 20 volt between 2 points and Q is 400 coulombs, like 400 microcoulombs. So just convert the microcoulomb into coulomb, and the electrostatic potential difference will be what? Work done upon charge. So delta V will be equal to W by Q. Substitute the value of delta V, that is equal to 20 here, and work done upon charge value is 400 to 10 to the power minus 6. So you will get the work done for value is equal to 20 into 400 into 10 to the power minus 6, that is equal to 8 into 10 to the power minus 3 joule. So this is your answer. This was a simple question. Just you have to put the formula and you will get the answer. Okay. Now example 3 is also there. So this is also similar to this question, but here you have to find out what? Work AB by formula of Q delta V. Okay. And here also you have applied the same formula Q delta V. So the formulas are same here. Okay. The question is similar. So I hope that you can do this by yourself. So electrostatic potential due to a point charge. This is the next topic. Let's see that what it says. So let P be the point at a distance r from the origin O at which the electrostatic electric potential due to charge plus Q is required. So suppose that you have any like charge here that has value plus Q that is situated on origin only. So you have to find electrostatic potential due to this charge where a point P is located on the x-axis. Okay, so here you have to find out the electrostatic potential, and the plus Q charge is your point charge. So you have to just find out the expression for that electrostatic potential due to this point charge on point P. So let what you do here. Let us assume that we have plus 1 coulomb charge at like infinite point. Okay, and yeah, let's move to the next slide. Yes. So here it is written clearly that the electric potential due to at a point P is the amount of work done in carrying a unit positive charge from infinite to point P. It means that if I have any unit positive charge this is at infinity. Okay, this is at infinity. Point test charge is at infinity. Then the work done required to bring that uh, point test charge to point P, it will be equal to what? Electric potential. Okay. So yeah, as work done is independent of the path, so as it is independent, we choose the convenient path along the radial direction from infinity to the point P. So we have chosen a radial direction, okay, without any acceleration. Let A be an intermediate point on this path where OA is equal to x. Okay, so let A be an intermediate path like point in this path, and where OA distance is what? Your x. Okay, so why have we have chosen like this only? That why we don't have directly calculated the work done by moving the point from infinite to P point? Why don't we have just applied that formula? Because we don't have any expression for that. Okay, because I have to see that what is the value of work done in this situation, and it will come by integration method only, because the value of work done and here force is also variable, and force is variable, so work done is like your coming as variable only. So that is why we have to integrate the this expression of force and what is the displacement. So that will give us the value of what? Electrostatic potential here. Okay, so let's move to the discussion. So suppose that you have a point this point charge at infinity, and you move it in at any intermediate point to A. Okay, and now you have to move it to the point B now, which has distance from A equal to dx. This is very small distance between A and B. So I have to this A point is x distance from O point. Okay, this is x distance. If I have to move now dx distance from A to B, what is the work done in that process? If I will calculate, so I can find out the expression for like variable force or variable work done here. Okay, let's see that how it comes. Okay, so yes, the electrostatic force on a unit positive charge at A is given by. So yeah, for like I have already told you that force value will be equal to kq into 1, because force is what? K q1 q2 by r square. So here k is there, and q is any your q is your charge value which is at origin, and unit positive charge has the value 1 coulomb. So that will be kq1 upon x square, because A point is what? At x distance from O. So that is why this expression will come here. So here it will be written that x equal to kq upon x square. More work done in moving the charge through a distance dx. So I have just told you that dx is the small distance between A and B point. So small work done will be equal to what? dw will be f dot dx, and f dx cos 180 will be applied here, because the work that force applied is opposite to the direction of your displacement. You can see here also. I will show you that yeah, this force is just a second. Yes, if you move the charge from here to here, this point. Okay, so you are doing the work done against this force, like this this force. Okay, force is in this direction only, like your electrostatic force, and you are doing the work against this force. So the expression for your work done due to field, I am applying the like work done formula due to this electrostatic field. So that will be equal to minus of F dx. Okay, why? Because the angle between this F and dx is dx displacement is in this direction. So angle between them is 180, and cos 180 is minus 1. That is why it is integral of minus f dx. And now we will substitute the limit here. Okay. So yes, let's do the calculation parts like in the like forward action. So yeah, small work done in moving the charge through a distance dx from A to B is given by dw is equal to f dot dx, which is equal to minus f dx, and dw is minus f dx coming here. So total work done in moving a unit positive charge from infinity to the point P is given by. So yeah, from infinity to the point P, the expression is given as your like integration of the first initial point is infinite of your unit test positive test charge. The final point is what? Small r, because your point P is at a small r distance from your origin. Okay, that is right. The final distance point is small r, and your work done is already I told you dx. So by putting and substituting the value, you will get like expression like this: a q by x square dx. What is the integration of like 1 by x square? That is integration is 1 minus 1 by x. Okay, you already know that integration of 1 by x square is what? X power minus 2 integration. So x power minus x power n integration is x power n plus 1 upon n plus 1. So here you can get x minus 2 plus 1 upon minus 2 plus 1. So that is equal to minus 1 by x. So that is why it is coming minus 1 by x here. And minus sign was already there like in previous step. So one minus and another minus will cancel out, like it will if you put the limits, though you should put the first like lower limit then your upper limit. Okay, you can see also here, just a second. Yeah, here you can see that. Yes, here q by 4 pi epsilon naught is there, and minus sign will come inside the bracket, so it will be make it plus sign. So then you can put the first upper limit then lower limit. Okay, so q by 4 pi epsilon naught is there, and this minus sign has come here, and it makes it plus sign. So it will do 1 by x limit 1 infinite to r. Now substitute the limits, you will get work done is equal to q by 4 pi epsilon naught into r. Okay, because if you substitute the limit r here, it will give you 1 by r only. Okay, q by kq by like 1 by r minus 1 by infinity. 1 by infinity is 0 only. So kq by r is the your expression for final expression for like electric potential difference or electric potential at point P due to a point charge. So from the definition of electric potential, this work is equal to the potential at point P. So I have got the expression for electric potential at point P. Okay. I hope that you got this question, that how I solved this. So let's move forward and see what is the next thing in this. Yes. Yeah, so it is written that a positively charged particle produces a positive electric potential. Yes, so it is obvious that a positively charged particle produces a positive electric potential. That is, you have already seen that a positive charge will produce like field like positive, having positive energy, and negatively charged particle produces negative potential, electric potential. Okay, so that is obvious. Here we assume that electrostatic potential is zero at infinity. So this is also, I have told you that electrostatic potential at infinity is considered as a reference point and is equal to zero. Equation 4 shows that it is your equal distance from a point charge q, value of v is same. It also shows that if a point is equidistant from point q, then the potential electric potential is there equal. Okay, and electrostatic potential due to a single charge is spherically symmetric. So that is also obvious that the electrostatic potential due to single charge is spherically symmetric. Okay, figure given below shows the variation of electrostatic potential with distance. So we will see the figure and figure out it that how the like behavior of the graph of V and R here. Also, the variation of electrostatic field with distance, that is E is equal to directly proportional to 1 by R square. So that we have already studied that E is directly proportional to 1 by R square for like point charge. Okay. So yeah, let's see that what is next thing. So here it is the graph of your like V and E with respect to distance. For so here just see that both the graphs are like what they are hyperbolic in nature, but your slope of uh, like your this V versus R graph, that is your V versus R graph here, slope at the upper side in the range like your 0 to 1. Okay, because 0 to 1 it is more steeper, and after that it will become less having less slope than E versus R graph after one point. Okay, it is obvious because you know that V is directly proportional to 1 by R, and E is directly proportional to 1 by R square. So if you substitute here a value between 0 to 1, if I substitute like zero point 0.5, so V directly proportional to zero point 0.5, 1 by zero point 0.5, and E is directly proportional to 1 by zero point 0.5 square, so which has more slope. This has more slopes. That is why it has steeper, like more slope in the this region. And in this region, like if you have value greater than your 1, okay, if the value R is greater than 1, so you have V directly proportional to like 1 by 2, but E will be directly proportional to what? It will be like your yes, E will be directly proportional to 1 by 2 square. Okay, that is your expression for what? In the region after 1.1, like 1 point. So in this region, you can see that your yeah, E is like V is directly proportional to 1 by 2, but E is directly proportional to 1 by 2 square. So this value is greater. This is greater, and this is smaller. Okay. Why? Because 1 by 2 square is obvious, giving you a greater value. Denominator is here more. So this will be your just a second. Yes. Yeah. See here, you have here this below 0 to 1 region. This was your electric field is directly proportional to 1 by zero point 0.5 square, and your V directly proportional to 1 by zero point 0.5. So here this value is greater. Okay, electric field value is greater. This is greater only. So that I already told you that this is greater and this is smaller. Okay, so it has like less slope and it has more slope. So that is why you can see that E graph is steeper here. So that is why E have more slope. So will be steeper from V. So I have told like in the opposite way, but it is like V will be steeper than V. And the in the region greater than 1, the E graph will be less steeper than V, because E is coming here what? E is coming here smaller value. So the I have written greater, but they smaller, and V will be greater value. Okay, greater, because 1 by 2 is greater than 1 by 2 square. Okay, so I hope that you got this point, that how the graph is drawn and why it is above B versus R graph in the region 0 to 1, and after that it is above below the B versus R graph. Okay, E versus R is below the V versus R graph in the region 1 to infinite. Okay, so that is all, like this topic is all about this. Let's move further and delete the drawings here. Okay, see the example of 4 here. So what is that? What is electrostatic potential at the surface of a silver nucleus of diameter 12.4 Fermi? Atomic number Z for silver is 47. So here it is given that your small r, that is the distance between what? Distance between nucleus of like silver nucleus and your surface. Okay, so that is equal to 12.4 by 2. Small r will be 12.4 by 2. Why? Because diameter is 12.4, so distance between the nucleus and surface will be equal to radius only. So 12.4 by 2 is 6.2 Fermi, and 1 Fermi is equal to 10 power minus 15 meter. So if you like multiply it with 6.2 into 10 power minus 15 meter will be the answer, and Z will be equal to here 47. It is given obviously here, it is given here. So by charge of the nucleus will be equal to what? It will be equal to Q equal to ZE. That is equal to atomic number into your electronic charge. Because nucleus has the total charge equal to what? Atomic number into whole atomic number. That is number of photons or electrons into the electronic charge. This is 1.6 into 10 power minus 19. So therefore, electrostatic potential at surface will be equal to what? V is equal to 1 Q by 4 pi epsilon naught R. So after computing this value, you will get the answer as 1.09 into 10 power 7 volt. Just do the calculation, you will get this answer. Okay. Yeah. Let's move further and see what is the next thing. So there is example 5 is telling that a point charge Q is placed at point O as shown in the figure. So here point charge is placed at point O, and is there a potential difference VA minus VB positive, negative or zero? So we have to tell that whether the potential difference between point A and B, that is VA minus VB, is positive, negative or zero. If Q is positive, first part is for Q is positive and second part is for Q is negative. So let the distance of points A and B, points A and B will be like from charge QV, RA and RB respectively. So this is assumed here in this question that this distance is what? This is your RA and this is your RB. Okay, this is RB. So here a potential difference between point A and B will be what? This is equal to VA minus VB. VAB will be written like this only. VAB will be like VA minus VB, in that will be equal to KQ, capital Q, up into 1 by RA minus 1 by RV. You already seen that this is the expression for your point charge. So that is why we have written like this. Now RA will be equal to OA. Why? Because it is already seen here that OA distance is RA and RB is equal to OB here, and RA is less than RB here. So RA is obvious here that it is you can see also RA is here less than RB. Now this implies that 1 by RA is greater than 1 by RB. So 1 by RA will be greater than 1 by RB. This will be greater than 1 by RB. Therefore, what are you getting like sign of this expression? 1 by RA minus 1 by RB will be positive value. Okay. So VA minus VB depends on the nature of the charge here. 1 by RA minus 1 by RB is positive here. Like this value is positive here. Okay. This value is entirely positive. So VA minus VB depends on the nature of this charge. This charge has positive value or negative value. That will decide the value of your VAB, that whether it is positive or negative. So in first part, VA minus VB will be positive when Q is greater than 0. Because Q is here positive only, so the whole expression will be positive. And VA minus VB will be negative if Q is negative. So this will become negative because Q is negative here. For first part, you are getting your VA minus VB positive, and in the second part, it is negative. Okay. I hope you got this question also. So let's move further and see what is the next thing. Okay. Now electrostatic potential due to a system of charges. So this is similar to that we have studied in the your previous topics, electrostatic force due to system of charges. So that is just similar to that only. So let there be a number of point charges Q1, Q2, Q3 up to Qn, at a distance r1, r2, r3 up to rn respectively from the point P. So there are many charges like q1, q2, q3, q4 up to qn, and they are situated at a distance like r1, r2, r3 like this. So here q1 is this distance is r1. Similarly q2 for q2 this is r2. Okay, this is r3. So you can like see and decide that this is the distance between the points and the charge, like the point P and the charge. Okay. So V1 will be equal to what? Q1 by 4 pi epsilon naught into R1. R1P is obviously here R1 only. So that will be equal to like KQ1 by R1. Similarly, V2 will be KQ2 by R2. V3 will be KQ3 by R3. So similarly, you can find out RBN also, that is will equal to KQN by RN. Okay. So let's move further and see what is the superposition principle here. So if we obtain relative potential at point P due to total charge configuration as the algebraic sum of the potential due to individual charges. So if you calculate the net potential here, so V will equal to what? V1 plus V2 plus V3 plus dot up to Vn, because it is scalar quantity, so we directly add them. Okay, we will get KQ1 by R1 plus KQ2 by R2, like that only. So that expression will be finally written like this: K times, just a second, K times in your uh, summation of I1 to N Qi upon Ri only. That is your expression. Okay. If you expand it, then it will be like a KQ1 by R1 plus KQ2 by R2. So that I have written in the summation form here. Okay. The net electrostatic potential at a point due to multiple charges uh, is equal to the algebraic sum of the potential due to individual charges at the particle point. So I already told you that it is scalar quantity. So all the potential due to each point charges will be added like individually and sum up to the whole potential there. Mathematically, it is expressed as like this V net is equal to integrate like a summation of 1 to n I1 to n Vi. So that is equal to V1 plus V2 plus V3 that I have told you. Okay. So example 6 is here given. Let's try to solve this example, and after that like this example we will continue our lecture in the next class, because today we have already covered many things, and due to time constraints we will see the next topic in the next class. Okay. So let's try to solve this example. What it says: 2 point charges of 4 microcoulomb and minus 2 microcoulomb are separated by a distance of 1 meter in air. So there are 2 point charges that have the values 4 microcoulomb and minus 2 microcoulomb, and they are separated by a distance of 1 meter in air only. Okay. So medium air is what? Air. Find the location of a point on the line joining the two charges where the electric potential is 0. So we have to look at any point P which has such a distance from these charges where electric potential is net electric potential is 0. Let the electrostatic potential be 0 at point P, that is we have assumed there, and the two charges separated by a distance small x. Okay. So it is obvious that if you chosen any point outside this two charges, like if you have chosen here, if you chosen here the point, then the electrostatic potential will be uh, this will be due to this charge, it will be positive only, and this will be negative only. But the distance is here varying. Okay, distance will be varying here, and we have to just find the point where the net electrostatic potential is 0. Okay. So if you choose here the point, okay, if you choose here the point like P point, and this is X, So this will be equal to what? 1 plus x. Okay. Just a second. Yeah. So that will be like distance between these points. Okay. Just a second. Yes. Yes. So one distance will be like x meter and another will be 1 plus x. Okay. So if you solve that expression, then you can get like another value of x here. But we have to just locate the point between these two charges. We have assumed that is between these two charges. Okay. So let's solve this point for point P. So yeah, let's do this. So you can have like two or three values here, but we have just located a point P in between the two charges. Okay. So yes, after like solving it at point P, we have Vp is equal to V1 plus V2. Okay. So that will be equal to V1 plus V2 due to this charge. There is V1 and this is due to this charge. So apply the formula that is equal to K Q1 by R1 plus K Q2 by R2 equal to 0. The summation of k q1 plus q1 by r1 plus k q2 by r2 will be equal to 0 only. So if you like now cancel out the k from both sides taking common, so you will be remaining with 4 into 10 to the power minus 6 by x. Okay, because at this point you have the distance x from the 4 microcoulomb charge, and that is equal to k is like k cancel out, that is equal to 2 into 10 to the power minus 6 upon 1 minus x, because this distance is 1 minus x only. Okay. And the charge value is minus 2. So after like going this side minus 2, it will come plus. Okay. So yeah, after solving this expression, what you will get like as 2 1 into 1 minus x equal to x. So 2 is equal to 3x you will get, and x is equal to 2 by 3. So electrostatic potential is 0 at a distance 2 by 3 from the your charge 4 microcoulomb. Okay. So why he has not taken the point P in distance like here only, or like this side or this side? Why not taken? You can like take here also this point, okay, or here also this point. Let's find out that why is not taken here. Okay, we will solve this also. Okay. So if you have taken the point here, like P point here, so your distance, this will be what? This will be x, and here this distance will be what? 1 plus x. The whole distance will be 1 plus x. Okay. So now if you apply the electrostatic potential formula here, you will get the expression like 4 into 10 to the power minus 6 upon x. Okay, equal to, yeah, now this will be equal to 2 into 10 to the power minus 6 upon 1 plus x will be there, because now the distance has become 1 plus x here. So I am like solving for any point that will be left hand side. So now you solve this, 10 to power minus 6 and minus 6 will cancel out. You will get the expression as 2 into 1 plus x equal to 2 into x. Okay, x only. Sorry, not 2x, but x only, because 2 will be cancelling out 4 by 2 times. So after solving it, you will get 2 plus 2x is equal to x. So from here, you will get x is equal to like, yeah, minus 2. So this distance will be like minus 2. So minus sign is showing that this is left hand side from this point. So this will be minus 2 distance. Okay. So 2 distance from this. So if you substitute now here minus 2, so what you will get? Okay. X is coming here minus 2 only. So basically you are like getting this expression as negative here, 1 minus 2. Okay. So that will be not sufficient, like giving you the sufficient answer here. And this will be minus 2, like this will also minus 2. This will become minus and this will minus. So that will be not the perfect value for you. That is why he has taken the point P in between the these charges. Okay. So I hope that you got this question. And yeah, that was the last question today. We will continue our discussion in the next lecture and see the next topic. What is the next topic? Till now, I hope that you liked the today's session, and also you have learned many new things today. And I will clear this all ranks. And in the next class, we will continue our discussion and see that what is the next topic. The next topic is electrostatic potential due to an electric dipole. So we will continue this in the next lecture. And if you have any type of doubt or any type of solution, you can comment in the chat box. And also, if you want any private session or one-to-one session from us, you can also tell us only. Okay. So thank you for today's lecture and have a great day.